Hello, my dear student. Welcome once again the course number 1, that is the electrodynamics in M.Sc. First Physics. In previous video we will complete the module number 3. That one point will be remaining, that is the Hertz potential, and that point will be covered in next some videos. In this video we will start the module number 2, that is the energy, force, momentum and electromagnetic waves equation. Okay, these are the module number 4, and in that module, that is the first point is the energy relation in quasi-stationary current system. In the module number 2, that is the energy, force, momentum relations and electromagnetic waves equation. In first point is the energy relation in quasi-stationary current system. Then next point is will cover in magnetic interaction between two current loops, and that point we will see in TY-BSc. Then next point is the energy stored in electric and magnetic field, and next point is a pointing theorem. This theorem we will prove in TY-BSc. Then it is a part of that is the wave equation, that is a general expression for electromagnetic energy, then electromagnetic waves equation, and that electromagnetic waves in stationary medium, and that reflection and diffraction of electromagnetic plane waves, and lastly that is the skin effect and skin depth. This point will cover in the module number 2, that is the energy, force, momentum relations and electromagnetic wave equations. In that first point, we will in this video we will start the first point, that is the energy relation in quasi-stationary current system. Energy relation in quasi-stationary current system. What is meant by quasi-stationary? Quasi-stationary means that is the slowly moving energy in a magnetic field. What is meant by quasi-stationary? Quasi-stationary means slowly moving energy in a magnetic field. Slowly moving energy in a magnetic field. This is the quasi-stationary. Then we will obtain the energy relation in that quasi-stationary current system, that is the slowly moving energy in a magnetic field. Let's start the expression. Then consider a process in which a battery with electromotive field. Consider a process in which battery with an electromotive field E dash is feeding energy to both heat loss into a magnetic field. Means E dash is the electromotive field is feeding means to provide energy both into heat losses and into a magnetic field. Heat losses because energy, that system is a quasi-stationary, it is slowly move. That means in that process that heat will be lost. That means this electromotive field E dash will feed or will provide of that system into a magnetic field, and that is electromotive field E dash is feeding both into heat losses and into a magnetic field. That represent that equation, that is a J is equal to sigma E plus E dash, E bar plus E dash. With the help of this J is equal to sigma E, that is the microscopic forms of Ohm's law. First equation are J is equal to sigma in bracket E plus E dash, where J is the current density, E dash is the EMF of the battery, that is the electromotive force or electromotive field, and E is the field derived from the potential, These are the first equation, that is the J is equal to sigma E plus E dash. Okay. Then in that next step, taking scalar product of equation, that equation 1, taking scalar product of equation 1 with respect to J. That means in LHS side, taking scalar product with respect to J, that means J dot J is equal to sigma as it is E dot J plus E dash dot J. Second step are the taking scalar product of equation 1 with respect to J, we get J dot J is equal to sigma E dot J plus E dash dot J, and therefore J dot J is a J square is equal to sigma E dot J plus E dash dot J. This step as it is. Then this sigma will multiply, transform of that side, it will be the divide, and that J square divided by sigma is equal to E dot J plus E dash dot J. In that next step, this term, that E dot J which transform of that side, it will be the plus in that side, transform that side, it will be the minus, and equation 2 are the E dash dot J. E dash dot J is equal to J square divided by sigma minus E bar dot J bar. That is the equation number 2. This E dash dot J is equal to J square minus E bar dot J. That means this E dot J, transform that, it will side, and it will be the minus. Okay, these are the equation number 2. Then significance of that equation number 2 are the LHS of equation 2, that means E dash dot J, that LHS of equation 2 represent the time rate at which battery does work. Rate means dash, E dash, that equation 2 represent the time rate at which battery does work. LHS of equation that represent time rate at which battery does work, means that will provide a electromotive field, that is a E dash. Okay. Then the first term of RHS, J square divided by sigma, that the first term of RHS represent the joule heat loss in the current carrying medium. First term of RHS means J square divided by sigma is the represent the joule heat loss in the current carrying medium, and the last term of RHS at the rate at which fade into a magnetic field, energy fade. This E dot J represent the rate at which energy is fade into magnetic field. Okay, but we are see the relation, if all fields are in quasi-stationary. Okay, we will obtain the energy relation in which system? Quasi-stationary. Means if all fields are quasi-stationary, that is slowly varying the displacement current, that is slowly moving in a energy field, or slowly varying the displacement current may be neglected. That means this displacement current term will be neglected because all fields are quasi-stationary. Then Maxwell fourth differential equation is del cross H is equal to J plus delta D by delta T. But field are quasi-stationary, that means this displacement current, that current will be neglected, that means delta by delta T will be neglected, and but displacement current term will be neglected, and that above equation becomes del cross H is equal to J, means the value of J, that is J is equal to del cross H. With the help of this value, J is equal to del cross H, equation 2 becomes, equation 2 are the E dash dot J, means in J is replaced by del cross H, J is replaced by del cross H, and J is replaced by del cross H. Equation 2 becomes, right, E dash dot del cross H is equal to del cross H bracket square divided by sigma minus E dot del cross H. Okay. Then equation 2 that J is replaced by del cross H. Then in the next step, taking volume integral on both sides of above equation. Taking volume integral on both sides of above equation, and that volume integration over volume V, E dash dot del cross H dV is equal to integration over volume V del cross H square divided by sigma dV minus integration over volume V E dot del cross H dV, and that is equation number 3. But this last term, E dot del cross H, this last term, we will obtain the expansion of this last term then by using the vector identity. Vector identity is del dot E cross H. Now by using vector identity is del dot E cross H is equal to H dot del cross E minus E dot del cross H. But we will obtain the value expansion of E dot del cross H, means minus E dot del cross H, transform it that side, it will be the plus, and that del dot E cross H transform, it will be the minus, and that the last equation are E dot del cross H is equal to H dot del cross E as it is, and this del dot E cross H transform that it will side, it will be the minus del dot E cross H, means the value of E dot del cross H is a H dot del cross E minus del dot E cross H. But the value is integration over volume V. Then next step, this last equation, taking volume integral of that equation. Let's see the taking volume integral on both sides of above equation. We get volume integral E dot del cross H dV is equal to volume integral H dot del cross E dV minus volume integral del dot E cross H. But we know that the Maxwell third differential equation is del cross E is equal to minus delta B by delta T. And next, the convert this second term of this del dot E cross A, second term of RHS of above equation into surface integral. This term del dot over volume integral del dot E cross H dV, this term, this second term of RHS will convert the surface integral, means volume to surface, then by using the Gauss divergence theorem, and that equation becomes that integration over volume B E dot del cross H dV as it is equal to integration H dot this del cross E is equal to minus delta B by delta T minus delta D by delta T delta B by delta T dV minus, and this last term, this second term of RHS is converted into surface integral by using this Gauss divergence theorem, and that conversion are integration over surface as E cross H dot ds. This equation is reduces to that equation. Two changes are the put the del cross E is equal to minus delta B by delta T, and this volume integral is converted into surface integral by using the Gauss divergence theorem, and that conversion is integration over surface as E cross H dot ds. But that cross product E cross H falls in electrostatic because system with Cauchy stationary. This cross product of will be false in electrostatic, means neglected or deleted in electrostatic because system will Cauchy stationary. Then last term of RHS will be neglected, and remaining term are integration E dot del cross H dV is equal to minus H dot. This minus will be separate out, minus integration over volume B H dot delta B by delta T dV, and using above equation 3 becomes, means the value of integration over volume B E dot del cross H dV, and that equation 3 are this equation. This term value will be obtained, and that's equation 3 is integration E dash dot del cross H dV is equal to integration over volume B del cross H bracket square divided by sigma dV. This minus, and equation 3, this term will be minus will be plus integration H dot delta B by delta T into dV. This is equation number 4. And the RHS of first term of equation 4, RHS of first term of, that means this del cross H bracket square divided by sigma integration represent the rate at which Joule heat loss, and second term this H dot delta B by delta T represent the energy fed into the field. This is the physical significance of this RHS of these two terms. Okay, but we know that next step, but we know that the functional relation between H and B, functional relation between H and P is given by, and that relation are UM is equal to 1 by 2 1 half integration H dot B dV, equation number 5. That is the functional relation between H and B, and that is UM is equal to 1 by 2 integration H dot B dV, equation number 5. But we know the relation, that is the B is equal to del cross A, and we know A bar is the magnetic vector potential, and put this equation B is equal to del cross A in equation 5, then equation 5 becomes UM is equal to 1 by 2 as it is integration H dot, there is a volume integral H dot B is the del cross A dV. Then we will obtain that expansion of that term. We will obtain the expansion of that term. Which term? This H dot del cross A dV. 1 by 2 integration H dot del cross A dV. Then now by using the vector identity, this expansion of this term, then now by using the vector identity, and the vector identity are del dot H cross A is equal to A dot del cross H minus H dot del cross A. This vector identity we will use, and the expansion of this term H dot, that means this term transform that side, it will be the plus, and this term transform that side, it will be the minus, and that the value of that expansion of H dot del cross A is equal to A dot del cross H minus del dot H cross A. But this term are the volume integral, then taking volume integral on both sides of above equation, then volume integral H dot del cross A dV is equal to integration over volume A dot del cross H dV minus integration del dot H cross A dV. Okay, but system are Cauchy stationary, that means put del cross H is equal to J. Let's see the in in this video, that is the system is quasi-stationary, that means Maxwell displacement current dabba by dabba t term will be neglected and put del cross H is equal to J, and second term, this term del, this is the volume integral, it's converted into RHS of second term is converted into surface integral using Gauss divergence theorem, and that equation becomes, above equation becomes del dot H dot del cross A dV is equal to integration A, this del cross H is equal to put J, that means A dot J. Let's see, integration over volume A dot J dV minus integration, and this volume integral is converted into the surface integral. Last term will be integration over surface S H cross A into ds. Okay, this equation, that's two changes are there. That is the del cross H is equal to J, and second term of RHS can be converted into surface integral by using Gauss divergence theorem. Then, but system is quasi-stationary, then second term will be neglected, that means this H cross A is neglected, and remaining term H dot del cross A dV is equal to integration A dot J. This is the value of H dot del cross A, and by using this equation, equation 6 become, equation 6 are um is equal to 1 by 2 integration over volume V H dot del cross A dV, means this term, and the value will be integration over volume V A dot J, and equation 6 is um is equal to 1 by 2 integration over volume V A dot J dV, and this is the required equation for energy relation in quasi-stationary current system. This is the required equation, that is um is equal to 1 by 2 integration A dot J into dV. This is the required equation for energy relation in quasi-stationary current system. Okay, in next video we will discuss the next point, that is the magnetic interaction between two current carrying loops. Thank you.